Okay. A few seconds. So welcome to the final WHCGP of the semester. And we're very happy today to have Sam Raskin from the University of Texas at Austin talking about recent progress in the geometric Langlands program.
Thank you. Thank you for the invitation. So a couple things before I get started. So the first is a technical thing. I'm writing on paper under a camera, everyone. And I'm just going to make mistakes with this sometimes, and things might be on a little bit too high or something like that. Just unmute and tell me. That's the easiest thing that works for me. And the second thing is about what I hope this talk will be. It's the first time I've tried giving a talk like this. I kind of, maybe I a little bit algorithmically generate talk titles sometimes, but I don't really want to discuss a ton about actually recent progress. What I would rather do is give a little bit of just an overview. I know this is a non-specialist audience, and I'd like to say something just kind of about the overall background for the subject, and we'll see how successful that is. Yeah, but the work I'm going to talk about here is this is all joint work with Dennis Gaitsgory, and some part is joint with many people. So I'm going to try and get them in alphabetical order. So Rinkin, Dario Beraldo, Chen, Keem Fersman, and Dennis, and then Kevin Lin. Okay, so for me, the starting point of the subject is kind of the following sort of thing. So there's some starting observation, which is that there's a classification theory of, and then I should put some technical words, connected split reductive groups. And reductive groups, this is because I'm an algebraic geometer, but these are in canonical bijection with connected compactly groups. So if reductive groups sound scary to you, you should think in terms of compact Lie groups instead. So when I say GLN, you should think of a unitary group instead. And this bijection, this classification kind of has the following shape. Has the following flavor. Well, following data. So first, there's lambda, a lattice, aka a finite free abelian group, finitely generated free abelian group. There's a certain set delta, which is a certain finite set. And maybe I'll say here, so that it has a dual, which I'll call lambda check. So this is just maps from lambda to z. there's a certain finite set called delta. There are embeddings of delta into lambda and also into its dual. And then there are some axioms that this should satisfy. Sort of combinatorial axioms, you say. These data satisfy. So in other words, this so for a group G, reductive group, we speak of its root datum. I should say this this classification can be refined. It ends up being very rigid. So these the key examples of these groups G. So G could be like GLN, SLN. It could be PGLN. It could be a special orthogonal group or a spin group, or it could be a symplectic group, or it could be one of 5 families, 5 exceptional families, or sort of, I would say, minor variations on these. For instance, you can take products, or you could quotient GLN by, or let's say you could quotient SLN by a finite subgroup that wasn't its full center, which is Z mod n. That gives you PGLN, but if n were 4, you could quotient by a Z mod 2 instead of Z mod 4. You know, but minor variation. So there's basically just a complete list. I prefer not to. I mean, this list is important. It's good to keep in mind, but let me emphasize not so much the specific list and more the combinatorial data which is attached to it, which in some sense is a little bit more rigid. You can sort of forget that there's this classification. You shouldn't really forget these things, but you kind of can. And this passage from the group to its classification data, it's not super complicated. This lattice is going to be the characters of a maximal torus in G. This will be the non-zero character. Well, for this embedding, it'll be the non-zero characters that appear in the adjoint representation. This embedding involves certain SL2s mapping into the group. But it's a little bit, you know, you see there's a certain amount of just, there's a certain recipe that the wisdom of the years has taught us, and it's not like, I mean, you can argue about how natural it is, but it's something that works in this setting and not like something more general. And there's a sort of a miracle that falls out from this, which is that these root data are sort of manifestly dual. They sort of, well, let me say it this way. They have a manifest Z mod 2 symmetry where you exchange lambda with lambda check, and you keep delta the same, but you exchange the 2 embeddings. So I said that there's some axioms. Promise the axioms are also completely symmetric. And so the sort of upshot is that for a group G, for a reductive group G, there's some other group around which is called, well, G check, and this is called the dual group or the Langlands dual group. This is, take the dual of G check, you get back G. And the relationship, I would say, between G and G check is really, it's through their combinatorics. Not like their group theory or their representation theory. Or any such thing. And sorry, and I should kind of quickly give some examples. So wait, I should have given myself more space. So G and G check, just very briefly, the dual to GLN is again GLN, the dual to PGLN is SLN, the dual group to an odd spin group is going to be an even symplectic group, and hopefully I have those numbers right. Yeah, and the dual to an even spin group is going to be an even orthogonal group, and it's a little bit, I don't know, it's sort of a little bit of a funny construction. You can just apply it to the list, you get some answers, but again, I said, you can keep the list in mind or not, it's your choice, but I think it's convenient to think in terms of, directly in terms of the combinatorics.
Sam, is that SO2N mod at center?
Thank you. Absolutely. And so the kind of the basic question that I think people were wondering, like, I can't say exactly, first half of the 20th century, it's like, what is the role of this duality for reductive groups? So, again, they weren't called reductive groups 100 years ago, but people knew compact Lie groups, they knew this classification, they knew many things. And there's this basic, again, this basic operation. And if you just think like, you have G versus G check. So does this G check have somehow, like, is there any relationship between the representations of G and the representations of G check? No, there's not. Is there any, at least, of course, some cases G is equal to G check, and you can say in special cases, they're just equal or something like this. But like that's not a satisfying general answer. So, does G check parameterize some kind of group theoretic data that has to do with G? Again, it doesn't. There's not a simple way to just pass from this group to its dual group. I mean, you can pass to the combinatorics, which itself, it's not so complicated, but it's a little involved, and then passing from the combinatorics to the group itself takes some thought. And so there's this, just clearly you see it from the classification theorem operation, and it's a little bit of a stumper. Like, we believe compact Lie groups are like a fundamental object of nature, and then we just say like they have this duality and it must have some role. What is the role of this this duality? Question makes sense? Maybe I'll pause for questions for a moment. So I guess the answer.
I have a question.
Yeah.
I mean, you're going to answer the question, what does it mean to be What's the meaning of the duality and of Langlands between the dual group given by the symmetry of the root diagram?
Yeah, I mean,
Okay, great.
I don't know that I'll give a satisfying answer, but
Right,
yeah,
great, fantastic. Okay.
that's. I mean, I'm not gonna say anything that wasn't known. You know,
No, I know that, but I don't know it, so it's great.
The answer appears to be, you know, this plays, I mean, this plays a fundamental role in the Langlands program, role in the theory of automorphic forms. And related topics. So this is overall called the Langlands program. I want to give a kind of very quick, and I should say, well, okay, I'll give a very quick, hugely simplified overview of this in a simplified special case. So I'm going to take some curve, I usually call it x naught, defined over a finite field fq. So this is a smooth projective curve. So you can just, if you're not used to these things, fq is finite field with q elements, and this is just something that looks like a curve. Maybe it's like y squared equals x cubed plus 1. It should be smooth, so that's why I did the plus 1, and it should be projective, so you should really add a little bit at infinity in that kind of picture. But otherwise, it's just that I wrote down an equation that makes sense with coefficients in this particular field. Could have added some other elements from this field in the equations. But it's that kind of thing. So there's something called, I guess, for my own funny reasons, I'll write bungee of FQ for the set of G bundles on this curve x naught. So what does this mean? So if G is GLN, these are rank n vector bundles. For G being something like the you know, SON or a symplectic group. These are G bundles. Sorry, these are vector bundles of appropriate rank with suitable bilinear forms. You know, that kind of thing. For E8, I don't know. I can't give you a good answer, but there's a definition and something very systematic, and somehow when we understand the group well, the G bundles don't look so scary. And so I'm going to say a special class of automorphic forms, whatever those are, is the space of compactly supported functions on this bungee of FQ. So these are functions with finite support. And this is, so yeah, I could call this like space of automorphic forms or something. So again, in much more generality, well, I should say special class, technically I'm talking about unramified automorphic forms here. And in the real world, somehow, and real, I mean, in the technical sense, people care a lot much more about things like the rational numbers and their extensions, instead of, I'm sort of implicitly using the function field of this curve as my global field. And this is the simplest setting. Already, this space it's only really just last few years being understood well. But it's the story. It's definitely starts with the rational numbers, and that's where a lot of the special fun happens. But that I've sort of said my piece about this. So the goal is to somehow understand the space of compactly supported functions. So I should also add that when the group G is GL1, this bun GM, well, there's maybe like a Z around, but otherwise this is basically the points of the Jacobian of the curve. So some finite set times Z. And it was really, and so I mean, studying characters on the Jacobian is the theory of class field theory. They had the idea that generalizing somehow the study of the Jacobian to the space of maybe higher rank bundles was a good idea for getting more information about function fields and ultimately about arithmetic. And I think he was the one who really kind of initiated the study of these kinds of sets. So yeah, so there's a kind of key construction, which is due in some form to Hecke. I'm not going to say exactly what this is, but due to Hecke, it's due to Satake, and I think in this form it's a little bit due to Langlands. And I'll just say sort of very briefly what it is. So for each point of the curve, there's a certain canonical action of K0 of G check, acting on this space of automorphic forms. So this is like okay, this is the Grothendieck group of representations, thought of as a Grothendieck, let me say, ring of representations. So there's a sort of story here that's happening purely near the point, and maybe I'll just write the word. So this is given by the Satake isomorphism
of this vector space of functions.
Yeah, so this is just an algebra. This is a vector space, and I'm saying that this thing's naturally a module for this vector space. Or, I mean, maybe I should tensor up with, I'm sort of not being careful about my fields because it's a distraction. And this is really a ring over Z, but dynamic generated ring.
Wait, K0 of rep of A, what's A?
There is no A. This is G check.
What?
G check.
Where's A?
Well, what's G?
Oh, well,
Oh,
this-
bun G. Okay.
yeah, that G. Yeah.
Oh,
So automorphic
G
forms
check
depend on G.
at the
Then all
dual.
of a sudden,
G hat is the check is the dual. Dual.
G
group.
check is the dual. Exactly.
I was dual.
So there's some
Okay.
fundamental thing
Oh,
happening here with
I
the
see.
Satake isomorphism, which I'm not going to say what it is exactly because it's
Here.
a distraction. But what
This-
I want to say is that
This G and this thing is G. Action. Dual group object.
so the Satake isomorphism gives some kind of in the grand scheme of these things, simple connection between the group and its dual group. And one kind of structure it leads to is for every point on the curve, it gives rise to some action. So these are called Hecke operators. So I don't know, it's called a Hecke action. And so this is some kind of starting point for this connection between G and G check. And yeah, other questions at this point? See, there's some chat. Yes.
So, Sam, how much is this like? Is this like a deep construction, or is it just from the combinatorics of Dynkin diagrams?
It's something in the middle. So I can so there's content to it, which is this Satake isomorphism. Okay, maybe I'll just write something over here on like a side piece of paper that'll then get erased, and we'll see how it works. So this group algebra of rep G check, it's somehow it has a basis by the irreducible representations of G check, and these are what are called dominant coweights. So there are certain coweights. There's a few of them. So a certain set of these. There's something else that's around, which is a certain kind of double coset space involving G. And there's a map from here to here, which sends a coweight lambda check to somehow the point in here, which is like, I would say lambda check of t, where t has the same meaning. So this might be something like t to the n, t to the minus n for SL2. Putting this a little heuristically. And this map turns out to be a bijection. This is called the Cartan isomorphism. And for GLN, it has some basic name that I'm forgetting. It's this general theorem about PIDs, something super familiar. It's sort of, well, up to conjugating something on the left and on the right, you can write it in any element of GLN of fraction field of a PID in a certain preferred form, like sort of descending powers of the uniformizer. This has an algebra structure. So this gives some kind of bijection between this space and, if you want, like z-valued functions on this double coset space. Well, compactly supported functions, finitely supported functions. And this guy has an algebra structure. And it turns out that for group theoretic reasons, these kinds of double quotient spaces of a group by a subgroup on both sides actually also itself always has some kind of algebra structure. Well, up to existence of measures that don't really matter here. And what Satake did is he said, this algebra structure over here matches that preferred so-called convolution algebra structure on the right-hand side. So that's the content of the Satake isomorphism. This thing will just for stupid group theoretic reasons act on the space of automorphic forms. It's not obvious from how I wrote it, but it's obvious once you think about it. And then you would apply the Satake isomorphism to get an action involving this group G check. So you could think of it as a calculation of something like this in terms of the Langlands dual group. And something where somehow the combinatorics matched, and then there was the theorem saying that the algebra structure is also matched. In fact, I said that there's a bijection, but that's not the right bijection to take. So if you take that one, the algebra structures won't match, and the actual algebra structure is more subtle. So the actual somehow isomorphism is more subtle than that. Other questions? So the problem that Langlands posed is to, well, I don't know if it was he who posed it. But the problem that Langlands and Harishchandra and Gelfand and Hecke and definitely work of Hecke. So the problem is to diagonalize the Hecke operators. So since like tensor product of representations is commutative, this is a commutative algebra. I said that this happens at a point, but if you do it at two different points, they don't interact with each other at all. In other words, they commute. And so you get this huge algebra of a huge commutative algebra acting on this vector space. And it makes sense to try to kind of diagonalize the operators. The Langlands conjectures are very precise. They're sometimes they're very precise. They're technical, and sometimes a little sprawling. But the spirit is that the answer to this problem involves representations of what's called the étale fundamental group of X naught. So this is somehow, okay, already writing it better. You should take the V group, if you know what that is, into this group G check. AKA it involves G check local systems on X. So this is a yeah.
Question.
Yeah.
Does pi 1 of X naught mean X with that as base point or X with that as a puncture?
X naught, that's a great question. And it's because of notation I'm just using because I'm used to it and not because it's super relevant to the talk. X naught for me is defined over a finite field. So for me, kind of geometry happens when you're over an algebraically closed field, and kind of arithmetic things happen when you're over a non-algebraically closed field. So I would say pi 1 of spec FQ is the Galois group of FQ, which is roughly Z.
Yeah, Z hat. Yeah.
Z hat, yeah. And the difference between that I'm writing here is the difference between Z hat and Z. So in fact, if I did this properly, I would see a Z and not a Z hat.
Okay.
But so this fundamental group of X naught is going to map to Z or Z hat because X naught maps to spec FQ. But then it has this fiber, which is going to be the geometric fundamental group. And that's going to have 2G many generators, and they'll satisfy relations like you expect. And that doesn't quite define it in this case, but it's pretty close to defining it. And that's just because of finite characteristic issues. So I would say like that kernel, that geometric fundamental group, is the thing that's more like the fundamental group as we know it. But somehow this X naught itself, you can think of FQ as being kind of like a circle, and this X naught is some kind of 3-manifold fibered over the circle, whose fiber at some point, which is like that FQ bar, the algebraic closure, is the surface.
Okay.
That you really care about. And that's a common heuristic in the subject that can be useful when you're thinking about this. But yeah, this is something more complicated than the fundamental group of a curve. And that somehow reflects the arithmetic nature of this. So we'll see something simpler pretty soon.
So you're interested in the action of that Z hat on the geometric fundamental group? Is that part of the problem?
Yeah, this thing, like if you, yeah, this will be a, you know, again, with asterisks or something, this will basically just be Z hat acts on the geometric fundamental group, as you said, and this will be the semi-direct product. Assuming there's a point over this field, but
That could be a pseudo-Anosov action, which has eigenvalues. And then would the Hecke diagonalization be related to that somehow?
you probably start running into issues because these are really pro-finite groups and things.
Okay.
And this is, I'm writing
Okay.
G-check, but this is somehow, it's really going to be something, I'm hiding this, but this relatedly, my coefficients will really involve like L-adic numbers and things like that. Because I want them to have profinite topology, just like X naught does.
Okay.
Not X naught, just like Pi1 does. Sorry. But we'll kind of maybe come to more familiar things in a moment. Kind of wanted to give the overall starting point. So there's an idea of Beilinson and Drinfeld and many others, especially in the kind of classical case of the group GL1, which is that a lot of the objects that we're seeing here involve the geometry of curves. There's like these, we see the fundamental group of a curve. Everyone, you know, see people clicking on to this. We see these G bundles on curves. And the idea was that maybe there's something some fundamental, purely geometric. So like, let's say over algebraically closed, take this to mean over algebraically closed fields. Phenomenon that gives rise to you know, like this sort of this behavior in harmonic analysis. Or, you know, the field being somehow FQ bar or FQ or something. I said algebraically closed, so.
I mean, the conjecture is that you can explicitly diagonalize the Hecke algebra action. I mean, what's the behavior you're referring to?
My legal team won't allow me to say just a simple yes to that answer because of all of these things. But in certain cases, and that word explicitly is doing a lot of, you know, puts me on edge. But the overall expectation is yes. For again, with many asterisks, there should be, you know, attached to one of these representations, there should be an essentially canonical function on this space. And that function should satisfy some very special properties. And functions arising in that way, suitably understood, many asterisks on here should essentially span the space.
Okay, thank you.
Yeah. Many asterisks, but that is the spirit of the idea that Langlands is trying to get at, and that a lot of work has gone into turning that idea into a real plausible set of conjectures, which by itself, you run into various obstacles very quickly with this, if you take it too literally. Yeah. So in answer, so I guess I should say, so it's going to be a little bit of a weird story. So over characteristic zero fields K, an answer was given, was proposed by Beilinson and Drinfeld. The answer, it involves the following kind of spaces. So first, there's going to be this bungee, which is the stack parameterizing G bundles. I don't impose semi-stability conditions or any kinds of things like this. There's no, it's not a, you know, for people who really say I mean, I'm going to call it a space sometimes, but it's not a moduli space in the technical algebra geometric sense. This is the, you know, thus the stack. First of all, so again, for GM, up to things like degree and that line bundles have automorphisms, this is basically just the Jacobian, essentially an abelian variety, but for non-abelian groups, it gets quite a bit more complicated. So that's going to be kind of the first geometric object. And the second geometric object is going to be what I call Loxis G check, or maybe I'll start writing LS G check. And this is the stack parameterizing. Yeah, and I should say also, I'm using this word stack. I know not everyone loves it. Maybe I have to ask everyone to accept it. Roughly speaking, it's a space that parameterizes something. So like projective space is the space parameterizing lines. A sphere is a space parameterizing rays. Sometimes we parameterize things that have automorphisms. So something like a line, but not like embedded in a subspace. Maybe it's a line with a map to a space, but that map could be zero. So that would be the kind of thing that's like a stack. They're inherently non-Hausdorff and things like this. But it turns out in many situations, there's a geometric formalism for working with them. And the way it's easy to say the words I said, a line with a map to a vector space, it's often kind of not so bad to work directly with these stacks. There are new issues, but whatever. So this is going to be the stack parameterizing G-check bundles with connection. And these are somehow on X. So, and these I'll just call from now on G-check local systems.
Is there a sense in which a connection over something of dimension 1 is automatically has no curvature?
Absolutely, because yeah, exactly as you say. So here, everything's algebraic. So if you thought holomorphically, a holomorphic connection on a Riemann surface will be flat because its curvature is a two-form, is a holomorphic two-form on the curve. Yeah, I was going to say that too. Other questions? So now it's Satake, so I should say geometric Satake gives the following kind of structure on okay. I'm messing this up. I'm just going to scratch this out and we'll come back to it in a bit. So there's a couple ideas I need in order to kind of describe the story. So this is the sort of, there's a kind of general yoga here of how things work. And where that yoga comes from, I can't completely say, but in the time allotted. But there are a couple ideas, which is that somehow classic, like, if this is somehow the classical story and this is like geometric representation theory, which is kind of what we're starting to discuss, then if I have something like, a number, classically, here I'm going to see a vector space. And maybe this vector space in real life would carry an operator, and the trace of that operator would be my number, which is the kind of thing you should think. And well, if I stick a bunch of numbers together, then I get a vector space. And what I'll see over here in geometric representation theory instead is going to be a category. And usually the category will be sort of linear over whatever field was implied here, or here in number. And in real life, it's often quite a kind of objective. It'll be some derived category, but you can ignore that for this discussion. And what you should imagine is that this category will probably carry some kind of endomorphism, and there's a notion of trace of an endomorphism of a category, and it will give rise to that classical vector space. And by the way, that the automorphisms I'm imagining are sort of some Galois action for FQ bar versus FQ. That's the very technical kind of thing you should imagine. And I think that's the size I need to go on this list. And then there's another idea, which is that where before you saw functions on maybe the FQ points of the stack, this gets replaced by what's called the category of D modules on the space. I don't really have time to describe what this is. Well, I can say very briefly. Quasi-coherent sheaves with an action of vector fields satisfying kind of the natural compatibility that that the two should have. So an action by the sheaf of differential operators on Y, at least for smooth affine variety. But a little bit, I'm going to ask people to black box it and would say, if you really want to study this stuff, you should study what D modules are in detail, but I don't think I can say anything super meaningful about them in this time, but it's some kind of formalism. And in many ways, this analogy works very well. You can do certain things with functions that you can do with D modules, and it's a robust formalism. And so now there's going to be this analog of Satake. Okay, so first, there's going to be some kind of analog of the space of automorphic forms. And this is going to be the category of D modules on Bun-G. This is a category. Now we have this analog of Satake, and this is called geometric Satake. And this is going to say that now this monoidal category of representations acts on the category of D modules on Bun-G for every chosen point in my my ambient curve. And a little bit, and so this is this is called the Hecke action. And a little bit naively, I want to say that the goal is to diagonalize this action simultaneously for all points. In a certain kind of higher categorical sense, and there will be a couple issues that we run into along the way. So first, categorically, we have to enhance this a lot. This needs to be enhanced, and I'm just going to say a couple like words about what's going on here. So yeah, I should say everything that follows is so this is all kind of after ideas of Gaitsgory. this next little segment. So, sort of.
I forgot what D modules over Bun-G meant.
So let's pretend like Bun-G was like affine space instead. So like some algebraic variety.
Okay,
Let's say I replaced Bun-G by A1.
yeah,
These would be modules over the Weil algebra in one generator. Do you know what that means?
yeah,
Okay, so generators T and DT, and they satisfy kind of Heisenberg sort of relation.
thank you.
And there's it's that, but said coordinate free, higher dimension, and also in a stacky compatible way. It's that kind of thing.
Okay.
Are there questions? Okay, so very briefly, there exists a sort of universal source of Hecke functors. Which it's denoted rep G check Ron. Ron is a person's name, and it's for sort of Ron space, Ziv Ron. And this is the space of finite subsets of
It's finite subsets.
of this X. It appears in, quantum field theory, and that's as far as I understand where it was first really considered. Maybe I'm wrong about that, but plays a big role these days. But that's what it's doing. And the idea is that somehow, whenever I have some finite set of points, so this will be some kind of monoidal category. I have a natural functor, rep G check, and then I'll tensor it with itself S many times, sort of once for each point in here. And I'll get a functor like this. So you can imagine, like, I'm somehow saying for every point in the curve, this big category receives like a functor from this rep G check to there. In fact, whenever I had 10 points, I would get a tenfold tensor product of them. And it's rigged to have that kind of property, and also to allow these points to sort of vary and collide in suitable senses. And it's a little technical, but it's just a formal gadget here. And let me just say the Hecke action extends to an action of rep G check Ron.
Is that basically just saying that, the actions at the different points commute?
It's saying more than that. It's saying something. It's this kind of, like, at a technical level, this kind of statement encodes like the specific construction of the commutativity constraint in like geometric Satake. So it's like the fusion thing is important here. Does that make sense, Travis?
I guess so, yes.
So like one kind of thing you can do is like you can form this Beilinson-Drinfeld Grassmannian over like X squared. And if you give me two representations, I can like attach a perverse sheaf onto that space associated to those two representations. And like its restriction away from the diagonal is sort of the box product, and its restriction on the diagonal is going to involve like the convolution. And it's like that kind of construction is needed in order to really properly give this action.
I see, thanks.
So it encodes that they commute, but it encodes more also. Like it's something about the geometry of F and Grassmannians go into it. Yeah. In other words, I could say it's like the geometric answer to like why these things commute. Okay, so this extends to here. So on the other hand, there's a natural functor from this rep G check run to the space of quasi-coherent sheaves on the space of local systems for G check. And let me explain what this is for a second. So natural, and it'll be like monoidal, symmetric monoidal. Somehow, so if I fix a point in the curve, so the composition ended up getting myself convoluted here. The functor like this. So this I can think of as quasi-co of BG check, which I could also think of as quasi-coherent sheaves on the space of local systems on a small disk around the point X. So BG check is the classifying space. If you think about local systems on a disk, technically algebro-geometrically, this is the formal disk. On a small disk, well, there's no local systems, but they're all trivial, but that one local system has some automorphisms. And there's just this formalism of stacks says things work like this. And this is pullback along the natural restriction map that takes a local system on X. Let me just write this to a local system on the disk. Now, there's a theorem of Gaitsgory that says the action of this rep G check run, this Hecke action, on the category of D modules on bun G, factors through a uniquely defined action of this category of quasi-co of Lopsis G check. So in other words, here I have, some basically algebra, some other algebra, a map between them. You should think of this map as being sort of surjective, if you were thinking in terms of algebras. I'm saying that, and we also have some module for this algebra. It's this category of D modules. And I'm saying that action factors, the non-trivial assertion, but it's very much in the spirit of the Langlands conjectures.
Can you say again what this last symbol in Gaitsgory's theorem means?
This one?
All of that. Yeah.
All of that? Great. So this is the moduli space of local system, moduli stack of local systems in the sense I said, vector bundles with connection or G bundles with connection, G check bundles with connection on the curve. And this is the category of quasi-coherent sheaves on that stack.
Oh, okay. Thank you.
I'm about 5 minutes.
Yeah, I see that I'm out of time. So in other words, we can think of this Hecke action as an action of the space. So this is already very much sort of in the spirit of Langlands's conjectures. We see that this Hecke action factored through the action of, so to say, a smaller algebra, factors through something and of more like global nature. It doesn't depend on a point, it depends on the whole curve. We see that this category of quasi-coherent sheaves actually sort of secretly acted on this category of D modules on bun G. The sort of meta conjecture maybe, which is due to Beilinson-Drinfeld, is that actually D modules on bun G sort of approximately equivalent to the category of quasi-coherent sheaves on the space of local systems on G check. So this was refined by Rankin and Gaitsgory to a proper conjecture. And their conjecture says the following. So there's just some kind of notation that I think a lot of people find very off-putting, but the basic things to know here are that this category of quasi-coherent sheaves, so there's like some kind of homological algebra. So if you think in terms of like modules over like a polynomial ring, sometimes you only care about, let's say, like finitely generated modules. Arbitrary modules are just like formally unions of finitely generated ones. So for any practical question, it's probably just a question about a finitely generated one. On the other hand, it's useful to talk about non-finitely generated modules. Like if you think about module over a K algebra, it might not be finitely generated. You might want to restrict to think of it as a vector space over K, but it might not be, finite dimensional. And this is very similar here. So there's some operation int that means like sort of take formal unions of objects. And there's a theorem following Thomas and Chabot and others that this category of quasi-coherent sheaves, it's obtained by that from something called the category of perfect complexes. There's something bigger, which is called indco of log-sys G check. And this is defined to be ind of coherent complexes. And this indco nilp, well, maybe I should say it this way. This indco nilp is of this same nature, but there's some kind of series of embeddings. These are certain coherent complexes, just meaning bounded complexes, all of their cohomologies are sort of locally finitely generated modules over rings. Perfect complexes satisfy that property. And there's a certain category that was picked out in the middle. In fact, the definition was kind of forced by some conditions in Langlands' program. But this is the notation that is stuck. And the theorem kind of in progress with the attributions I said is that this conjecture is true. Let me say some kind of remarks, just very briefly. So the difference between like quasi-co and this indco nilp kind of is related to many sort of if you want, like, call them kind of functional analytic subtleties in the usual Langlands program. And maybe I'll just call that a remark and call it a day. I'm over time, and that's sort of, I think, all we've got time for right now. So that's what I got.
All right. Let's thank Sam for a beautiful talk. Questions?
I just wondering what the status is. So what's this last step that you're doing with Dennis now? Is that done, or are you still finishing it?
We're still writing it. But
And what is it actually? What's the last remaining step?
I mean, it's to compute what this module over this algebra is. In other words, it's yeah. I mean, that's what what is your question?
Well, I don't know. I just had the impression that there were lots of progress over the past several years, and it had proved, I thought, some version of this for GL general linear groups, etc. And then, am I getting it wrong?
No, okay, so you're definitely getting it right. So Dennis kind of announced a while ago this theorem for general linear groups, and I wasn't really able. I was kind of hoping to do it, but ran out of time. So relating these two things might look kind of intimidating, but actually, given this spectral action and this sort of idea, like if you think in these terms and then just remember that you should correct it, it's actually not so hard to construct a functor. So this operation of Whittaker coefficients gives you some kind of natural functor from D module on Bun-G to this category because of the spectral action. However, Whittaker coefficients were really, they're sort of Fourier coefficient kind of thing. So if you've seen classical Langlands program stuff before, you probably saw the Q expansion of a modular form related to some Galois representation. And this Q expansion is some version of taking Whittaker coefficients of an automorphic form or automorphic sheaf. And so those were really poorly understood for general reductive groups before. For GL2, they're very easy to understand. It's just sort of usual Fourier theory in some sense. For GLN, there's a trick to understand them, and that was kind of key in what Dennis was proposing. My student Joachim Feersman and I had a result last year that kind of proved something non-trivial about these Whittaker coefficients for general reductive groups. And so that was kind of one of the starting points of this, this work, is that sort of after that, it felt like everything else should fall into place. There's actually been a lot of simplification. So what we're doing now for GLN is already simpler than Dennis's original proposal in a lot of ways. And yeah, that's kind of the status. So yeah, I mean, what you could say is, like, if you just squint and imagine the conjecture was like this instead, what you can say, there's a natural functor from here to here, and Joachim and I proved that it doesn't kill any objects. But you could still have that somehow, in fact, either side could be much bigger than the other side. And you can imagine that what Dennis and I are doing is somehow saying that some kind of multiplicity one result, like there's somehow a unique eigensheaf for each local system.
So it's not like you have like a case by case part of this analysis. You have to figure out some things for the exceptional groups individually or something like that.
Yeah, it is not like that. Oh, I should also mention that Beraldo and Schlenk and Kazdan have a result that can be used to do this also when, at least in some form, when the group is classical and simply connected. But that's not the approach that we're using. We have a little bit of case-by-case analysis with the curve. So it's very systematic once the genus is at least 3. But in low genus, there's a little bit of messing around that we do.
Okay, thanks.
But it's not about the group, except in the case of elliptic curves where SL, the type A, is treated a little bit separately from other types. But yeah, the exceptional groups or anything, you don't need to know the classification really, except maybe a little bit for elliptic curves.
That's great.
Other questions?
Hey,
All right.
well, what does this theory have to do with physics?
So maybe it's a long answer, but and I mean, somehow many people have written about this, like Kapustin and Witten are the big names in the subject. Justin Hilburn and I wrote a take in the introduction to our paper. But the overall story is that I said one role in nature of what what this Langlands duality for reductive groups is about. There's another answer that other people came up with separately, which is that attached to this group G, there's something called like Yang-Mills theory in 4 dimensions, maybe n equals 4 supersymmetric. And I forget, Montonen and Olive and who's the other name I'm forgetting. They proposed that there was something called S duality for this theory that said that this theory for G was the same as the theory for G check, exchanging many kinds of basic features of the subject. And it turns out that if you do the supersymmetric twistings of both of these theories, and you take the line operators in both of them, like you evaluate them on, you have this 4-dimensional theory, 4-dimensional quantum theory, and you can imagine evaluating it on a 2-manifold, compact 2-manifold, and that will give you a category. And because of the supersymmetric twistings, one version will be producing for you sort of this D modules on bun G, and the other will be producing for you something like quasi-co of Fluxus G check. That's the yoga. And that's the idea.
Quasi something on G check. What was the something?
The quasi-co, this Q-co that I'm writing. So it's just to say, you have 2 quantum field theories, 2 4-dimensional quantum field theories that should be the same. Both of them are twists, but different twists of this basic Yang-Mills theory that, is the standard model or something, and in one case, you evaluate this on, you evaluate these 2 theories separately, but they should really be equivalent theories. You evaluate both of them on a surface. One answer
The
is going
surface related to the 4-manifold.
no, just some genus G surface. I mean,
Okay.
and so the yoga is that a 4-dimensional quantum field theory, it attaches numbers to 4 manifolds, it attaches vector spaces to 3 manifolds, and it attaches categories to 2 manifolds.
Ah, okay.
So if I take this and I evaluate both of these on these 2 manifolds, I'm on the same 2 manifold. One of them should produce for me something like this D modules on bun G for that 2 manifold, which is really a complex thing. So maybe it's more of a holomorphic theory, and really I should really be evaluating these on, you should remember the complex structure, or you can, I don't know. One of them will be producing for me this category of D modules on bun G. The other will be producing for me this, let's say, quasi-co, because physicists aren't. So, and then of the space of local systems for G check. And this G is because it was Yang-Mills for G. This G check is because it was Yang-Mills for G check. And one twist will give me D modules, one twist will give me quasi-co. That's the sort of picture that is supposed to happen. If you consider what's happening on a circle instead of on a 2-manifold, you'll end up with things like the local geometric Langlands program, which is a different subject. So that's what I understand of the relation with physics.
Thank you. That's a beautiful answer.
All right. Well, on that note, let's thank Sam again for a beautiful talk.
Thank you.
Thanks, Sam. That was great. All right. Maybe I'll see you next week. Oh, he's going.
All right, thanks.
Good to see you,
So
Travis.
it's great. Good to see you too.